Hello, this is Ryan Woodward recording for Intel's Digital Logic course. This is Lab 3, Part 5. And in this part, we need to build a circuit that displayed inputs and outputs to the 7-segment display. Specifically, we needed to have two 8-bit inputs, A and B respectively, show up on 4 7-segment displays in total. But because they're 8 bits, we can't use two simultaneous inputs because we only have 10 switches on our DE10 light board. And so we had to come up with a way to accept the input for A, then accept the input for B, and then we needed to add those together and display that sum on the remaining two 7-segment displays. And so as you'll see in the demo, I have the value B on the first two 7-segment displays on the right-hand side, A is the 2 in the middle, and then the sum is the two 7-segment displays on the far left. And that's what it's supposed to do. We take an A and B, display them, add them, and display the sum. But this required some interesting finagling. I won't go through all of the code, and I don't have the Verilog simply because of the sheer amount of time I actually was going through trying to get this to work. But it wouldn't be too hard to basically build Verilog off of this, what I have so far, because there's a lot of basic fundamental circuits in here, such as this full adder, which I won't bother to go through, but there it is. The full adder 8-bit basically is an extension of that full adder. We basically instantiate 8 instances of a basic full adder, and then we have an 8-bit full adder. That's it for that. The BCD to 7-segment is the same as I've been using. And this rising edge and falling edge D flip-flop, I rather than actually making them more dynamic per se, I just created two basic D flip-flops and made them rising edge or falling edge. There is a really easy way to make them so the rising edge or falling edge determines based off what clock input you have, and I decided not to take that route. I just created two separate D flip-flops. They are literally the same logic, except one occurs on the rising edge and the other occurs on the falling edge, and that's the difference. I didn't want to have multiple clocks or have to finagle a way to make them actually read as rising or falling based on that, and so I just elected to do two separate D flip-flops there. And this circuit here, even though it's called D flip-flop, actually brings in those two edge flip-flops and reads in the value. So how this works is that you read in an 8-bit value. As you press the button, that value is read to the rising edge D flip-flop, and then that allows us to adjust the switches. For instance, if we were to enter 1, we could then press the button and rising edge display would print 1 for that value. And then if we were to adjust those switches again, maybe to value 3, and release that button, then the value 3 would be displayed on the falling edge displays. And so that's what this circuit allows us to do. It allows us basically to clock this circuit once, and on the rising edge, one display is populated for the rising edge circuit, and then on release of that button, the falling edge circuit displays are populated there. But there's not much more to that because we just create a port map of two D flip-flops, of those two D flip-flops, falling edge and rising edge respectively, that I mentioned previously. It is worth noting though that rather than having Q bar, I replace that with Q2, and I treat that as an output that I want to use rather than the inverse of Q itself. Specifically for the circuit, for this lab, this specific conglomerate of circuits, is this Lab 3 Part 5. I declare an AB switch in. This is our 8-bit input that serves for the user to basically input A or B, well, A then B, depending on the order of the button press. We have a clock input, a reset input, and the reset works through the D flip-flop as well. If we pass in a reset, this is connected to both of the D flip-flops, which both of these have a reset button, and if it is reset, the output will be 0 regardless of whatever other input is done through the data switches, which is these here. This is D, essentially. Then we have several 7-segment displays. These are for A, B, and sum, respectively. Then we have a carryout for the full adder, the full 8-bit full adder. And we actually won't see that go high until we add, I believe, 99 or something greater than 99. Or the sum is greater than 99. There we go. That's a better way to put that. And then below that, aside our components, we have 3 intermediate signals. It's A switch, B switch, and sum. And those go into these port maps here. We have our D flip-flop, we pass in the AB input, and that allows us to switch that, so we don't actually have to pass in 2 separate inputs. We clock that here with clock, then we have reset, and the outputs are those intermediate signals here, A and B switch respectively. We pass those then to the full adder. The sum will be in this other intermediate signal, and then we have the carry out here. And then finally, we display all that to our BCD 7-segment decoders here, and that's what you're seeing with these hex displays and the ports declaration and these intermediate signals we obtained above. All right, and that's it for part 5. Here is a demo. Thank you. All right, here is lab 3, part 5. We have A to B here on these 8 switches. A and B are these 8 switches there. Our carryout is this low LED on the right here. Our clock is this top button. And then we have B for these 2 7-segment displays, A for these 2, and sum is these 2. And just to show a few basic operations with the addition and the displays, how this will work is we press this to clock A, and when we release it, we will then clock B. So let's, for instance, make A 1. We'll see that the sum is adjusted. This is 1 plus 0, obviously. And maybe we want to make B 4. There we go. I just released the button. And now we have 4 in B, and 5 is the total sum. One thing I did not mention, but is this reset switch on the far left here. If we were to flip this, we will see everything go back to 0. All right, and we can actually do quite a few big numbers. Let's just increment this to get 31, and we'll add 31 to 31 to show 62 there. But for instance, the biggest we could do is 99 on these 2 sum displays. And the value for that, we could do 45 plus 54. So 45 is, going from right to left, is 1, 0, 1, 1, 0, 1. Then we'll clock A, we'll see 45 there. We can adjust the switches, now that they're all low now. And then we can put 54 in for B, which going from right to left is 0, 1, 1, 0, 1, 1. All right, and we'll release the button, and we'll see 54 be clocked to B, and our total sum now is 99, and that's the max we can do for these 2 displays. All right, and that's it for the demo. Thank you.